Good morning, everybody. Welcome to Calculus 1C. Today we're going to be talking about vectors, which play an integral role in this calculus course. To create a vector when given 2 points, where A is x of 1, y1, and z1, and vector B is x2, y2, and z2, subtract each corresponding component of the points to get each component of the vector. To find the length or magnitude of a vector, square each of the components, add them up, and then take the square root. A unit vector is a vector with a length or magnitude of 1. You can also make unit vectors by normalizing a vector or dividing each component by the magnitude. Listed here are some basic properties of vectors. Vectors following the commutative and associative rules, and when multiplying with a scalar, you can distribute the scalar, as can be seen in property 5, 6, and 7. For addition and subtraction, you will simply add and subtract the respective components. Now we're going to talk a little about lines and their parametric equations. Given a point P that is x, y, and z, and a vector that is a, b, and c, you can make a line using this general form for the parametric equation of a line by plugging in the corresponding values. However, when dealing with space and time, be sure to normalize the vector. This will be shown later on in a laser beam example in which time was asked at the end. Now for an example dealing with parametric equations, you have the question, find a vector equation in parametric equation for the line that passes through the point 5, 1, 3 and is parallel to the vector 1i, 4j, and negative 2k. You can plug in the values to get the parametric equation of x equals 5 plus t, y equals 1 plus 4t, and z equals 3 minus 2t. Now we're going to talk a little bit about dot product. It's important to note some of these key ideas like the definition, the property, and the theorem behind it, because dot product will be utilized in quite a few of the examples later on. To find the dot product of two vectors, given vector A being A1, A2, and A3, and vector B being B1, B2, and B3, multiply each corresponding component of the vectors and find the sum of those values. Remember that the result of a dot product is a scalar value. Dot product can be used to find the angle between two vectors as well. It is important to note that when the dot product equals 0, the vectors are perpendicular, and when the dot product equals 1, the vectors are parallel. In later chapters we will discuss the unit tangent vector, the unit normal vector, and the binormal vector. The unit tangent vector, the unit normal vector, and the binormal vector are perpendicular to each other, and this can be proven by doing the dot product. Now we have an example for the dot product. Here you're given two dot product, you can see that the vectors given here are written in different forms, so be aware of this. In this problem is written in the vector form, not parametric form. You're going to multiply each corresponding component and find the sum. You can see here that the sum is a scalar value and not a vector value. Note that if we actually write out everything using the third theorem on the last page, then we will be multiplying A1i to B1i, and A1i to B2j, and A1i to B3k. We can see that the I component dotted with a j component and the I component dotted with a k component will be equal to 0 because the cosine of 90 is 0. So in this example we have the vector A is negative 1, 7, and 4, and B is 6, 2, and negative 1/2. You can then follow the example and then what? Louder. Can't talk louder.
Get closer to.
Okay, so now we're going to talk about the angle between two vectors. You can see from the equations of the planes that the normal vectors of the planes are n1 is equaling 1, 1, 1, and n2 is equaling 1, negative 2, 3. This is going to come from the equation for the planes itself. The equation for plane 1 is just simply x plus y plus z is equaling 1, and so you'll get the normal from that being 1, 1, 1. And then for the plane 2, you have x minus 2y plus 3z. Those values will also give the normal for the second plane as being 1, negative 2, and 3. We're then going to use the cosine theta is equaling the dot product of n1 dot n2 divided by the magnitude of n1 times the magnitude of n2. Plugging in these values and simplifying, you find that the cosine of theta will equal 2 divided by square root 42. Using the cosine inverse, you can then plug in this value and you find that the angle will be roughly about 72 degrees. Now we're going to talk a little bit about cross product. To find the cross product of two vectors, create a matrix with the corresponding components of each vector in rows, representing the I, j, and k. You can then cover up each row consecutively and cross multiply. Be aware of your negatives. The j term should be multiplied by a negative, and when cross multiplying, the second term should be multiplied by a negative as well. We're going to do a little bit of a example here. So we have the vector A as being 1, 3, and 4, and the vector B as being 2, 7, and negative 5. Plug that into the matrix using the I, j, and k. You can then cover up the corresponding columns, giving you the little matrix that's shown right here. You can then simplify it down below into that form, giving you negative 43i plus 13j plus k, and that will be your cross product value. Now we're going to talk a little bit about component and projections. These play a very important role later on in examples where we're going to be finding the distance between like a point and a line or something like that. So when talking about scalar projection of B onto A, you're going to have the component of B onto A is equaling A dot B divided by the magnitude of A. When dealing with vector projection, it's a little bit different. So you have the projection of B onto A, that will equal A dot B divided by the magnitude of A squared times the vector of A. It's important to note that this is the vector of A because it is going to be a vector value. Now we're going to talk a little bit about skewed lines test. The skewed lines are lines that do not intersect. The best way to determine if two lines are skewed lines is to check if their vectors are not proportional, and then check that there is no point of intersection. Do a little problem now, kind of showcase this. We have the two vectors. Vector right here, which is 1, 3, and negative 1, and the vector 2, 1, and 4. And it's important to note that these are not parallel and they're not proportional. That way, therefore, they're not parallel. You can break up these vectors into parametric form as x equals 1 plus t, y equals negative 2 plus 3t, and z equals 4 minus t. You can also break up the following one and just change the s into a t, just keeps it a little bit more simple. That way you're not having two t values, as x equals 2s, y equals 3 plus z, and z equals negative 3 plus 4s. You can then simplify this and use just your x values, so you get 1 plus t as equal to 2s. You can then do the same thing with y, giving you negative 2 plus 3t equals 3 plus s. You then have the z, which is going to be 4 minus t is equal to negative 3 plus 4s. You can simplify this and you can show that t will equal 11 over 5 and s will equal 8 over 5. These values don't satisfy the third equation, therefore there are no values of t and s that satisfy this equation, so L1 and L2 do not intersect. Thus L1 and L2 are skewed lines. You can then find the distance between the two skewed lines. To find the distance, first cross the vectors to get the normal vector. This normal vector is perpendicular to both lines and between them. Then choose a random point on each line and create a vector between them. You can project this vector onto the normal vector to find the distance. We're going to do another skew lines distance problem. Here we have the direction of L1 is the vector v, which is 2, 3, negative 1, and it passes through point negative 2, 1, negative 1. The direction of L2 is going to be the vector w, which equals negative 1, 2, and 4, and it passes through point Q, which is 1, negative 1, and 2. It's important to note that the main step is to find parallel planes containing the lines passing through points P and Q respectively. To this end, we compute the normal vector as being the cross product between V and W. To find the cross product, like we talked about earlier, just plug it into the matrix form. You'll find that the normal vector will be 14, negative 7, and 7. You can then use this in the projection form to find distance. The distance will equal the projection of PQ onto N. And go back if you don't remember exactly what projection the form is, but you can see here that it's going to be the magnitude of PQ dot N divided by the magnitude of N. And you can see that it just simplifies to 11 over root 6. Now we're going to do distance between a point and a line. We have point Q here, which is on the line AX plus BY plus C. And then we also have point P, which is not on the line. We're going to find the vector between the point and the line. The directional vector in this case we will call U. And it will be the vector U is being A, B, and C. We then can project PQ onto the line and just follow the form that we've been talking about for a little while, and you can find that your distance will equal the vector U minus the projection of QR onto U.
So here we have an example of finding the distance between a point and a line given 2 points to form a vector. So we're given point P, which we have as 1, 1, 1, and we have a line formed by points Q and R, where Q is 0, 6, 8, and R is 1, 4, 7. So the first thing we'll do is find the vector between Q and R. So we have 1 minus 0, 4 minus 6, 7 minus 8. So we have this vector equaling 1, negative 2, negative 1. And next we'll find the vector between P and Q. So we have this equaling 0, negative 0 minus 1, 1 minus 6, 1 minus 8. So we have this vector PQ equaling negative 1, negative 5, negative 7. So to find the distance, we have the magnitude of H, of vector H, this one here, equaling PQ minus the projection of PQ onto QR. So what we'll do is first isolate this projection of PQ onto QR and solve for that first. So we have the projection of PQ onto QR equaling PQ dot QR times QR over QR magnitude squared. So plugging in our vectors, we have negative 1, negative 5, negative 7, dot 1, negative 2, negative 1, times 1, negative 2, negative 1, over the magnitude of QR squared. So from here we have 18 times this vector over 6, we can simplify this to equal 3, and we multiply it out, and we have 3, negative 6, 3 as our projection of PQ onto QR. So to find the distance, we'll have to do PQ minus that vector. So we have the distance equaling 1, negative 5, negative 7, minus 3, negative 6, negative 3. So we end up with a vector negative 2, 1, and 4. So to find the distance, we do the magnitude of this vector, and we end up with root 21. So here we're going to talk about some planes. So a plane in space is determined by a point, x, y, z in the plane, and a vector n that is orthogonal to the plane, and we call this orthogonal vector a normal vector. So we have the general equation for the plane, which is a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. So to find the distance between a point and a plane, we have a special formula for it. We're given the normal vector of the plane is a, b, and c, and we're given a point x, y, and z. We can find the distance where d is the absolute value of ax plus by plus cz plus d over the magnitude of the normal vector n, which is a square root of a squared plus b squared plus c squared. So we have an example of this where we have a distance between a point and a plane. So we have to calculate the distance from point P, which is here, 3, 1, negative 2, to the point 2x, to the plane, 2x plus y minus z equals negative 1. So the normal vector for this plane is 2, 1, negative 1. So we can make a line going through using this normal vector and that point. So we have the parametric equation for it. It's x, y, and z, where x is 3 plus 2t, y is 1 plus 1t, and z is negative 2 minus 1t. So to find the distance, we can do the point of intersection here. We can do the point of intersection, so we will find where the plane, we'll plug in this parametric equation into the equation for the plane. So we have x, y, and z represented here. You can see through the color coding. So we have 2 times the substitution for x, which is 3 plus 2t plus 1 plus t plus 2 plus t equals negative 1. And through some algebra, we find that t equals negative 5/3. So from here, we plug in negative 5/3 into the equation of our parametric equation of a line to get negative 1/3, negative 2/3, negative 1/3 as a point. And from here, we can find the distance between this point that we found here and this point by doing the distance formula. So we have the distance equaling about 4. So to find the distance between a line and a plane, we find the directional vector v of the line, then the normal vector n of the plane. If the line is parallel to the plane, the directional vector of the line will be perpendicular to the normal vector of the plane, and the dot product of the two vectors will be 0. Once you know that the line is parallel to the plane, you can pick a point on the line and it becomes the distance between a point and plane kind of problem. So here we have a distance between a line and a plane problem. We have to find the distance between this line where we're given a parametric equation. X of t is 1 plus t, y of t is 3 plus 2t, and z of t is 2 minus t. And the plane equation is y plus 2z equals 5. So we know that the vector of the line is 1, 2, negative 1, and the normal vector of the plane is 0, 1, and 2. So when we dot these two to see if they are parallel, we get, or perpendicular, we get 0, so we know that they're perpendicular. Now we choose a random point on line, so we say t equals 0, and we end up with a point 1, 3, 2, and we use the distance formula from the point to a plane. So we have ax1 plus by plus cz plus d over the magnitude of that vector. So we plug everything in, do a little algebra, and we have that the distance equals 12 over root 5. So to find the distance between two parallel planes, there are two methods. The first method is to pick a point on one of the planes and then use the method we discussed before using the distance formula to find the distance between the point and the plane. The second method is to make the plane equations have the same normal vector, then take the difference between the two values of d, and the absolute value of that value will give you the distance. So an example of one of these methods, we have this problem: find the distance between the two planes 4x plus 5y minus 3z plus 4 equals 4 and negative 8x minus 10y plus 6z plus 12 equals 9. So given these two equations, we can recognize that the normal vectors of the planes are actually proportional to each other, which means that the planes are parallel. So we multiply one of the vectors by negative 2 here, and so the vectors will be proportional. So now we have negative 8x minus 10y plus 6z minus 8 equals negative 8. So now we'll move the values of d over to the other side. So we have negative 3 here and 0 here. So now we take the difference between these two values, and we have negative 3 minus 0 equals negative 3. But to find the distance, we have to take the absolute value, so we have that the distance equals 3. So to find the point of intersection between a plane and a line, we plug the equation of the line into the equation of the plane and solve for t, then plug the t value into the parametric equation of the line to find the point. So for this example problem, we have the problem is find the point at which the line with the parametric equation x equals 2 plus 3t, y equals negative 4t, z equals 5 plus t, intersecting a plane 4x plus 5y minus 2z equals 18. So if we substitute the expressions for x, y, and z into the parametric equation of the parametric equations into the equation of the plane, we have 4 times 2 plus 3t plus 5 times negative 4t minus 2, 5 plus t equals 18. And if we do some simplifying, we find that t equals negative 2. And from here we plug t equals negative 2 back into these parametric equations of the line. So we end up getting that the point of intersection is negative 4, 8, 3. So here we have a plane and line intersection problem. We have p as 3, 2, negative 2, and a vector 1, negative 2, 2, and a plane represented by 5x minus 7y minus 3z equals 10. So the first thing we'll do is create a line, a parametric equation of a line using the point 3, 2, negative 2, and the vector 1, negative 1, 2. So we end up with x equals 3 plus t, y equals 2 minus t, z equals negative 2 plus 2t. And here we have the equation of the plane. So we'll substitute each of these values of x, y, and z into the equation of the plane. So we have 5 times 3 plus t, negative 7, 2 minus t, negative 3, negative 2 plus 2t equals 10. And from here we'll just simplify and solve for t, and we end up with t equals 1/2. So from there, we'll plug in 1/2 into the parametric equation of the line, and we'll get 3.5, 1.5, and negative 1 as our point of intersection. So when we have an intersection of two lines, when two lines are not parallel, they might intersect at a unique point. So in 2D Euclidean space, infinite lines always intersect. In higher dimensions, they usually miss each other and do not intersect. So if we're given the parametric form of a line A and line B, we replace all of the t in line B as s, and then we set x1 equal to x2, y1 equal to y2, and z1 equal to z2. So if we find that t equals s, then we know that the two lines intersect at that time. So here we have an intersection of two planes. We know that the intersection of two planes will always form a line. So here we have an intersection of two planes problem. So we're given the plane S1, which is 2x plus y minus z equals 4, and S2, which is x plus 2y plus z equals negative 1. So we want to find this line of intersection between the two of them. So the first thing we'll do is set z equal to t in both of the equations. And then we have the simplified version here of the two equations of the planes. And then we just keep solving the system of equations until we have x equals 3 plus t, y equals negative 2 minus t, and z equals t as our parametric equation of the line of intersection. So now we're going to cover some Mosh-approved problems from chapter 11. So the first, here we have Kepler's law, the first law, which states that the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus. So we're given UR equals cosine theta sine theta, and U theta equals negative sine theta cosine theta. So we know that UR dot U theta equals 0, so we know that they're perpendicular. So we'll find the derivative of each of these. So d theta UR equals negative sine theta cosine theta, and d theta U theta equals negative cosine negative sine theta. And we actually notice that negative sine theta cosine theta is the same as this, so we can say that d theta UR equals U theta. And here we notice that negative cosine negative sine is the negative version of this, UR, so we can say that d theta U theta equals negative UR. So now we have r equaling our position function r equaling r UR. So we'll take the derivative of this, and with some chain rule, we have r theta dot U theta plus r dot UR. And we'll take the second derivative to get an equation for our acceleration, and we have all of this junk here, and we'll just group the like terms, so we end up with the acceleration vector equaling U theta r theta double dot plus 2 r dot theta dot plus UR r double dot minus r theta dot squared. So here we have a laser beam problem. So a particle at t equals 0 is detected at point 213. So here we have it here. Then after it bounces off this surface, this plane right here, x plus y plus z equals 3, it's observed at point 222. So how long is the particle missing? So our first step is to get the normal vector of the plane and normalize it because we're dealing with time. And then find this point here, and then from there we can find how long it takes from this point to this point, and that should give us the amount of time it takes for the beam to get from here to here. So, as I said, our first step is to get the normal vector of the plane, which is 1, 1, 1, and we're going to normalize it because we're dealing with time. So the normal vector is 1 over root 3, 1 over root 3, 1 over root 3. Then we get the parametric equation for the line, this line right here, PD. So we have x equaling 2 plus 1 over root 3, y equaling the same thing, and z equaling the same thing as well. Then we plug this equation into the equation of the plane to find the point of intersection, or how long it takes to get to the point of intersection. So we have that time equals negative root 3. So we know it takes negative root 3 time to get to this point. But we want to find this point here. So we multiply this by 2 because we know that this is a reflection of this over the plane. So we multiply it by 2 and get t equals negative 2 root 3. So now to get this point, PC, we will plug in negative 2 root 3 into the parametric equation of the line, and we end up with 0, 0, 0 as this point, PC. So next, once we have this point PC as 0, 0, 0, we can find the equation of a line of this line here. So we're using point 2, 1, 3, and 0, 0, 0. We have a vector, negative 2, negative 1, negative 3, and we're going to normalize it because, again, we're dealing with time. So we have a vector, negative 2 over root 14, negative 1 over root 14, and negative 3 over root 14. And now we'll just plug those, this normalized vector and this point to get some equations for the line. So we have x equaling 2 plus negative 2 over root 14t, y equaling 1 plus negative 1 over root 14t, and z equaling 3 plus negative 3 over root 14t. So now we'll set this equation, this parametric equation of a line, to PC and solve for t. So we'll say that x, y, and z are all 0 because this point is 0, 0, 0. And then we'll just simply solve for t, and we get t equals root 14 seconds. So we know that it takes root 14 seconds for the laser beam to get from here all the way over here. So here we have an example of a billiards problem. You want to put the ball into a pocket at point S while it bounces off point Q and point R. So starting with points 0.5 and 0.5 and 2, negative 2, we can make a line L. So first we find the slope between those. We have 5/3. We make a line L that intersects point Q, so this line here. So that line equals y plus 2 equals 5/3 x minus 2. So once we have that line, we can find point Q by setting y equal to 0 because we know that point Q, the y value of Q must be 0 as well because the 2 points around it are also 0. So you can see that after we do some algebra, we find that point Q is 16/5 0. So now using 16/5, now we can find the line L2 using 16/5 0 and 2, 2, which we have up here. So we find that the equation of line L2, using the same method, is y equals negative 5/3 x plus 16/3. So from here we can find the intersection point of R by setting y equal to 1, and we know that R equals that the y equals 1 because that is the height of the billiards table. So by setting equal to 1, we can solve for x, and we get x is 13/5, so we know that point R is 13/5 1.